Okay, the contest starts in 17 seconds. I think I have everything prepared. It's AtCoder beginner contest. Sorry for that I didn't record anything for a while, but let's just get back to the contests. Okay, you're given a string from the following operations in this order: swap this and print the final. Yes, okay. So this is just straightforward. Also just see what characters you need to swap. 2i minus 1. Yeah, okay, I know how to do it. Just close this off so you guys can see. I think this is the case, but I think should be even, right? Given length, let's just see where's the judge. Submit caller ID. Each of the 10 persons performs following action once. The person I's ID has not called out yet. Call out person ID. In ascending order. Okay, so the just without being called, I will count them. So I can print the count, and then I will say that I will go if it's not being called. I will see out I as well. Bruno, am I not understanding? Has not been called out yet. Call out AI's person I's ID has not been called out. Maybe it's like this, just that. Alright, let me just understand the case here. I's ID has not been called out, so person 1 calls out person 3's ID. And what is the count? So enumerate the IDs of people whose IDs are never called out until the end. Yeah, if it's not called from I, not X. That's okay. You're given this and then some matrix, currently 1, 1. From now on, here is moving j squared to the right or below. I will be happy if the integers written on the squares he visits are distinct. Find the number of possible paths to make them happy. There's no modular, which means it fits into okay, we got accepting both of these into a long. So let's just call this. Oh, and we need to remember which have been called, right? Yes, so we need to like have like set of so it's what? It's a vector of what do I remember here? A map of I mean 10 should be DP, so 10. Yeah, I think this is better. Is it like a vector of maps, maybe? So this is a two-dimensional, and then you have like, you need for each of these to create this probably. It's like this. This is a set here. Yeah, okay. So we need dp of 0, 0 to be equal to 0, 0 to push back like a set of a 0, 0. Something like that. the answer is dp of n-1 dot size, right? Something like this is the answer. And then if I is 0, it means it's on the first row, so dp of ij. So for dp of ij minus 1, so for each of these sets, for auto s into this, for each of these sets, if s dot contains my, we continue, if not, dp of ij dot push back this set, dp of ij dot back dot insert aij. Because if j is 0, then we need for these sets to be purged. So now we're gonna do this. Else if I minus 1 is bigger or equal to 0, if j minus 1 is bigger or equal to 0. I think this should work. Okay, gets accepted. Tying rope. Okay, they're in ropes. One end of each rope is painted red and the other is painted blue. Okay, you're going to perform M operations of tying the ropes. Live operation. You tie the end of rope AI painted PI. Okay, with the end of. Okay. Find the number of groups of connected ropes that form cycles and the number of those that do not after all operations. Okay, so you just iterate over the, it's a little bit not, I mean, okay, the input is not that great, but okay, so each rope has like two okay, so we have like N and M, and then for each rope we're gonna have two things which pairs it. Jesus, I will do like this, two things that pairs, and first is like -1, okay? And then for each of these operations, is like row A color A, row B color B. Yes, color A color B. Color B. Okay, and then adjacency. So int CA is going to equal if CA is the red 0 and if CA is red then it's 0, otherwise it's 1. And color B is CB is red 0, otherwise it's 1. And then adjacency at A, at color A, I will hook up or I can do auxiliary nodes, right? I can do for each node I can do this. Adjacency, there are n times 2 nodes, right? For each of the n nodes, adjacency at I is equal to I plus one, like this, right? So like from here we go like that, and then here we hook up adjacency at A minus minus B minus minus. Alright, so 2 times I plus Ci, 2 times A plus Ci is where we hook A, and where we hook, so adjacency to this is exactly 2 times B plus CB, right? And then we want the baseline vector. To visit vector, if it's visited of I, we continue. Int C loops, not loops. And here is I. While adjacency at here is not minus 1. Here is adjacency at here. If visited here, then it's loops plus plus. just go to the next adjacency. If it's visited, loop is true. If it's not visited, loop is false. What's going on here? So there are 7 of these. This is oh yeah, so this and this is like yeah, if CA is 0, then let's see, let me fix this. the 0, so maybe we don't put it like this. We say if JCC of R here is -1, then we put this, else we put this. Now let's redesign this. If I do two-dimensional graph, I mean undirected graph, then I need to keep track of the parent, right? Why this doesn't work? When it's -1, we connect this and that. Oh, I see. We could always flip this, right? If A is like bigger than B, swap A and B and swap C, B as well, right? Okay, let's just do two-dimensional graph. So, I mean, unidirectional graph. Push back. Okay. This seems okay. Now here, adjacency at I, push back I plus 1. Adjacency at. Well, can I just use adjacency at I plus 1 push back I, right? If it's not visited, I'm going to ID the loops. Here I'm going to visit it. Let's just change this to like that. Okay, and let's retype this. Visited V has the same ID as me here. Visited me if it's already visited. Then I'll false. DFS of V and U. Return whatever false. Doesn't matter what return. Actually matters. Oh, and actually it's like this, that at U is my ID, right? So here this is the ID, and then if it's visited, so if CFS is like this, then oops, plus. Wait, I am printing it, right? Oh, 2 times, plus 2 times. Okay, this seems working. Given integers, find this should be accepted. Accepted. Given integers, okay, so what's the time? Yeah, that's slow. Given integers ax and m, find a to the power of I, and then sum them all up modulo m. So x is here. But there should be a closed form, right? I mean, the sum of a geometric what is this? Where the sum of a finite geometric sequence is the first, where R is right, is that geometric progression? Okay, let's code this. It's weird if this problem is that simple. The series is times 1 minus power of R, which is this is 1, isn't it 1? Always minus a to the power of x. Oh, modulo m. Oh, but it's not guaranteed. Oh, I didn't see that in the end, but yeah, okay. So it's not guaranteed that the module will be prime number. Okay. So there's something about powers here. Geometric series. So with like exponentiation, like binary exponentiation, there is a recursive binary logarithmic binary search thing that you can do. Yeah, this is exactly I mean, we could solve this in Python as well. So Plus no, it's reverse, I think. N is what? N B is the base, which means that it's like this. Yeah, this works. Okay, we're gonna take a look at how exactly this is made mathematically. I just want to solve. Given an integer n, not a. Okay, so let's see just the standings. Not less than 2. Find the number of integers b not less than 2, such that when n is written in base b, every digit is 0 or 1. Okay. I'm gonna just C, G, and EX. This is some DP. This here, triple index. Okay, you're given a sequence and give queries for each. The qth query gives you an integer L and R. Bring the number of integers triplets I, J, K such that they're inside this range. And they're equal. This is some data structure problem. So, okay, so what about segment tree? What do we know about this range? We can know how many of each numbers are in this range. We can't really know that, but we could sort the queries somehow. So square root decomposition. Just turn on this. So either square root decomposition, like most algorithm on the queries, or the like most algorithm you would have like a frequency array which you would just add these numbers to. You would just have pre-calculated sums for each of these, and then you would change the sum by how much does this change. So most algorithm does definitely work. What about segment tree? Segment tree would be a bit difficult to implement. But this is definitely most algorithm implementation. Okay. This here, you're given a tree. We find the minimum integer k such that you can paint each vertex in the colors to following conditions. And use any number of colors. Minimum integer k. For each color, the set of vertices painted in the color is connected and forms a simple graph. For all simple paths, simple path, not a graph. Okay, so simple path. For all simple paths on the tree, there are at most k distinct colors of the Oh no, 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 this is, I don't know. Like this maybe is some kind of century decomposition, but I don't know. I don't know how to solve this. So let's solve G. Triple index thingy. Triple index thingy. Okay, let's solve G. Hit. So when I add this index, it's like frequency of A1 plus plus. And then, so the difference is like the following. It's difference between A and B. So the closed form of C and choose 3, right? This is the closed form. That's A, and that's difference B. It's like the same idea. And now, so B is the new. Let's say B is the new. Then return dB minus dA, right? That's what we're gonna return here. This passes, so let's just submit it. See if it's fast enough to pass this. Then maybe we'll solve F as well. There seems wrong answer. Yeah, it overflows. Oh, that's bad. That's real bad, man. It just overflows here. It didn't time limit, right? No, it just overflow. I think now this should be correct. How did I write in there? Okay, that seems going. I mean, it's probably really hard to break most algorithm in this case because of the complexity. But So we solved this one. Let's see this one. Okay, so given an integer n not less than 2, when n is written in a base b, every digit is 0 or 1. Find the answer for t independent. So there's t independent test cases, and we need to write them in some bases. So what happens here? Y 0 or 1? So what happens here? But wait, how is this possible here? A finite number of desired integers not less than 2. Right. In base 20.4. It's like, what if a number is when you convert to another base, you divide by that base all the time, right? And you see what is the remainder. The remainder has to be either 1 or it has to be, so when you divide by that base, so it either has to be 0 or 1. So a multiple of that base is possible, like always. So when I have 12, although in base 6 it's 2. Yeah, so that doesn't work. It's like 2 0 or something like that, isn't it? Yeah. So it's 2 0 in base 6. This meaning that so it doesn't, it has to have reminder either 0, but it's not divisible. No, so if the base is 6, then it's like divided by 2. But if the base is 3, so it's like 4. There has to be some equation that does that. I'm not sure. Like, the problem is it n goes up to 10 to the 18th power. Can there be some kind of dp? Can there be some kind of dp here? So it's like you divide by the base, right? But you have to try a lot of bases. Or do you try a lot of bases actually? Maybe not. Like you want the first like 0, you want to try the divisors of that number, right? The divisors of that number are a lot. I mean, are not that a lot. It's like, and yeah, they're a lot. But you don't want to try all of them. You want to try the divisor that you want to try. So here's like this 11. It's like base 11. It has to be some kind of recursion. It has to be some kind of recursion that allows to do it like in about EX. So if K is actually really big, I'm thinking like a binary search on K here. Like for each color, the set of vertices painted in the color is connected and forms a simple path. So if you're taking a look at this like a DFS structure, you will have like either you start a new path here, and you end up every path, or you like you continue some path, or you just merge like these, like two paths like these, and then you say, okay, we cannot really use that color. So there are like 3 or 4 cases of what you can do in the DFS by like saying, and then probably for each case you would have like a DP structure, and then you will say, okay, how many colors have I used for this particular case? But the problem is this, like for all paths, and this is practically some kind of or maybe it's actually century decomposition here, but there's no idea why would it be century decomposition. It reminds me of something like heavy line decomposition, maybe like that, like the longest path you take, and then that would be for all simple paths there at most k colors. Find the minimum integer k. It reminds me when I have a line decomposition here. For each color, the set of vertices connected forms a simple path. So it is heavy light decomposition. So it's a heavy light decomposition problem. But heavy light decomposition so like you do heavy light decomposition, then what you print the number of paths for which that sets. Heavy light decomposition. Let's see what kind of code do we have here. I'm trying to figure out how to change this to count the so when you just have it like this here, RT is it's either from this, yeah, so I think this is the case. So I think I can solve it like this. Okay, so what do we don't really need to do? Process tree and this here. I mean, we'll never modify or query or do anything like that. Or probably just process, we don't need any of these. HLD values on the edges, I don't care, so like false maybe. HLD adjacency vector. Okay, so let's just okay, and then I need to go through this RT here. HLD at RT at I think that should be the answer. So like the minimum number, maybe this is not like really like optimal heavy line decomposition. And this is not optimal heavy line decomposition. This should be so I will just draw this tree here. So we have like 3, 4, 4, 5, 1. Wow. So this is like 3, 4, 5, 1, 2, 7, 1, 6. So if I see that this 0, 1, 2, let me just so 1 has a parent of 1, 2 has a parent of 1, 4 has a parent of 1. Okay, this is correct. This seems correct. And then there should be like 7 as a parent of 7. 6 has parent of 7, has parent of 7, 2 has parent of 7, so there's 4 of these. Okay. There is more optimal that this is picked up like that. So it's 3 here, but so this decomposition is not the optimal decomposition. May want to find like the centroid of the tree, and then from there put like a because this is not the most optimal. Yeah, even though if we have the century decomposition, we cannot merge it like this. What about if I say that, okay, the root is 0, but we say that maybe it's possible to merge but here it's no, it's like I don't know how to prove that there is a proof why this century decomposition is always log n, but the optimal century decomposition, not century decomposition, Heavily decomposition. So the parents of the heavy. But what if I get like if I get something to the furthest side possible, so or I get like a leaf or something. Maybe this will this works, but this doesn't. It doesn't, because like on each of these we'll have like let's see CPU algorithms how they handle this. Decompose everything here, but you can merge them somehow, maybe like with some kind of DP. Like optimally, what would it be? Optimal heavy line decomposition, so it has to be like optimal. No one quotes optimal halide decomposition. I don't know how, like, how should you quote optimal halide? Here again, subtree size. No one merges it like that. Like the first two biggest you merge it, or you merge it more like with some kind of dynamic program. I think like you merge the first two biggest. Maybe just sort them and just like try to merge them here. Like here, like sort. Oh no, not size. It's I guess sort adjacency at V, but with like a comparator. Like that. And then when you do this, it's like the first, the RT at but then like there's like this yeah, I know. There's like 19 seconds left. I mean, it has to be some kind of heavy light decomposition, but optimally arranged. Okay, let's maybe even binary search on K. Maybe even that would be possible. Even that would be possible. We do binary search over the S for the answer. Okay. We consider dynamic programming. So you binary search over the answer, but then like how you consider these rotations, let's say, or dynamic programming cases here, they're bounded by the heavy light decomposition. Okay. What about F? So the base B representation has this, I have this log n digits, okay? For each D, we want to find fast enough the number of integers B such that the base So I think I get the problem. So for each digit you get this, and then you know that, like, find fast enough the number of integers b such that the base b representation of n has d digits, each of which is 0 or 1. Base n representation of n. Oh, this is actually base n representation, right? Okay, this I would have never solved. No, especially like considering this. I mean, yeah, I don't know. I have to get better at mathematics. This triple index problem was good enough, but what's the online solution? So the MOS algorithm solves this problem. Also, it's intended to be solved with the MOS algorithm. Okay, so alright, I thought that there is some online solution. Okay, so the MOS algorithm is like this is the intended solution. So the tasks were okay. I mean, they weren't that bad, but still it took D a lot of time, and E, of course, just this, like, this mathematics. I didn't like getting down to it, but I should get down to why is this the case. But it's like actually just a way of like dynamic programming onto binary. It's not really dynamic programming, but it's something similar onto the binary exponentiation. It's like just remembering the things, and okay, so this problem was good enough, but G is really I think a good problem. This overflow here, I'm not proud, but yeah, it's a simple MOS algorithm, and yeah. So thank you guys so much for watching, and I see you in the next video.